There we go. Yeah.
Okay.
Yeah.
So I'm gonna pick the one that's off-centered. Just do a drag and drop in here, and then I'm gonna select. I can do either open or insert. So if I choose open, it'll basically try to bring it in, and it'll ask you, do you want to know if the file is in millimeter units or if it's in inch units?
Correct.
Would you know if it's in millimeters or it's supposed to be in inches?
It's a long one, and it doesn't make any difference. It's just
okay.
Yeah.
Okay. So one of the things we could do is check the stock extents around the part, and it tells that it's 12.7, which is on the X, and the length measures about 70 inches, and then the height measures about 7.9. So in inch units, if you try to wrap a box around it, that's what it measures for you.
Correct. It's way too big. I was scaling it down, but this is
okay. Yeah, we can scale it down by a certain like a ratio. We could do that in Rhino, and we can, for the purpose of demonstration, we can do that. So, okay, the first step is to open or import the file that you want to work with. The next step is basically go through the workflow in here. You can see that the part is off in space, so we can move this part over to the origin at the correct location and then orient the part. So if you take a look at it part from looking down from the top view, you want to make sure that it's in the initial orientation looks correct from the direction from which you would like to mill this part.
Okay.
Okay, so one of the ways we would do it here is if your rotary axis is about the Y, then the orientation looks correct. If it's rotary as in the X, you want to rotate the part by 90 degrees, so it's the center of rotation will be on the X axis.
Okay.
So on your CNC router that you put together, is your rotational axis parallel to the Y or is it parallel to X?
It should be the way it is, parallel to the Y.
Okay, all right, so we'll leave it the way it is. So the first step is to define the machine tool. We're going to be doing a 4-axis operation, so we'll change from 3 to 4. So you can do both indexed and continuous, and the configuration is defined as table, which allows you to basically turn the part on your rotary axis or rotate the table. And then we want to make sure the rotation axis direction is set to Y, so it can be plus or minus Y depending on how your rotary axis is defined and set up. So we'll do this in this process. Y and then pick OK. So that basically establishes your machine tool. The next step is to select your post processor. RhinoCam includes over 300 plus different posts right out of the box. The posts are either listed by name of your CNC machine tool or by the name of your controller. So in this particular step, I'm going to select Mach 3. That's what you mentioned during our conversation earlier.
Correct.
And then you can choose NC or CNC or TAP or whatever the preferred extension for Mach 3 is. Now, I would like to move the part over to the origin. There's a couple of ways you can do it. You can use the transformation tools in Rhino, or here I can choose align and pick set world coordinates. I can say set to the part box, put it in the mid Z, over down at the end. This actually puts the part right in the center line right there for you. Okay?
Yeah.
So we have the part defined as you see it, and then if you look at it from the front view, the 000 is over at this lower left corner. So if you want to flip the part over the other way around, we can do it in Rhino. It's just a simple rotation command to flip it over.
Yes.
Okay. Now I can see that there are features on this part that are dipping below the center of rotation. So let's go ahead and rotate this part over by 90 degrees so we can clearly identify the areas that it's, we can see the undercut, right? So you can see this undercut if you look at it from the right side view.
Yes.
So when we do our 4-axis machining operations, if you do like a 4-axis, parallel finishing, which is one of the methods, it's more like a projection type of method where the tool will not let you dip below the rotation center because the tool remains normal to the axis of rotation, so it's not going to dip below this. Now, just for the programming this section here, we can actually do an indexed operation just for this area. I'll show you how to do that, and then we'll also look at what are the other ways we can program it as well. Okay?
Yes.
All right. So step 1 is, after we have the part everything oriented, we'll go ahead and define the stock material for it. So I'm going to use box stock. and selecting copy model box will automatically compute the extents. Now, what would you like the length typically to be on this part? You want to scale it by half the size?
Let's just say 24 inches, or you could scale it 50% would be fine.
Okay. All right. So what I'll do here is select this model in Rhino and do a transform scale, or I can just do a scale. And then I can put the origin 0 and then say scale it by half the size. So now the model is scaled to 50% of its size right there. And then again, you can go back and realign it if you need to. You can put it to the mid Z and then the center, or to the south based on where you want the 0, 0, 0 to be placed. And that'll basically ensure that the 0 is right over here. And if you need to adjust it or move it, you can still use the transformation tools in Rhino to move the part around as you need to, right? So you can basically select it here, and you can use these tools to move the part to basically wherever you want the center to be placed at.
Okay.
Okay, so once you've established this, you want to build your stock material. And now you can see it's the length is about 4 inches, a little over 35 inches, and then the thickness is 6. So we can change this to maybe 4.5 inches on the X, which is the distance along the X, or I could even put in like 5 inches. And then the length, overall length, I could make it 40 inches. And then the height or the thickness, we could say it's going to be 6.5 inches. Okay.
Yes.
And then we want to align it. So we want to align the stock. So we want to align it so it's centered in both directions. If you take a look at it from the front view, the stock will be centered in not only in Z and also in X. So now the stock is fully centered around the part.
Okay.
And we can actually adjust the transparencies in here. Typically, when you're in the Simulate tab, the transparencies are set. There's 2 different modes in here. So typically it's set to being more transparent. So you can actually see the part and the stock within that. Okay. You can establish these transparencies. And then we go through the process of establishing the 0. So we can put the 0 over to the far left corner, set to stock, mid Z south. So it automatically compensates for this material that you have in here. Like, you can actually also model your, like a piece of block to hold the material in here, right? So you already have a support that's modeled in here, but if you want to also add something else in here, you could do that as well, okay? So to hold the piece. Now the next step we would want to do is, for programming this, if you do want to do like a, like a 3-axis operation where you want to typically you want to rough it from 2 sides. What I could also do here is put in a rectangle in here that basically represents the extents of the stock in here, right? So I'm going to basically throw in this rectangle, and then I'll select the rectangle and just extrude it. So you can use modeling. You can create solid modeling in Rhino as you're creating these geometries in here. So I'm going to say extrude curve straight, and then I'm going to just go right up to this point right here. And I can choose to do a solid, or I can just say just be a surface of extrusion. Okay, so basically I just drew a frame in here. I'm going to hold Alt key and then just drag this over also to the other side. So I can place it over here on the other end.
Okay.
So we have these 2 pieces defined in here, just like supports, and then I'm going to start my roughing process. So I can either create tools as I go programming these parts, or I could define and load tools from my library. So I can go ahead and say locate a library of tools. I'm going to go look for some tools in here, and let me go find, I may have it saved in one of the earlier versions or in a different folder in here. So let me go find some tools that we can load. I'll just go into the 2018 folder. I may have some tools in here. So I'll bring in a tool library for inches. Okay, I got about 14 tools loaded, and I'm going to go through the process of programming toolpath. So the first step is to do a roughing, and I want to rough it from 2 sides. So I'm going to go grab a tool for it, like a 1/2 inch end mill or a 3/4 inch end mill, set feeds and speeds, set the clearance to be automatic, and establish the cutting parameters. You can choose whether you want to do a linear cut pattern or an offset pattern. You can choose your direction of cuts. So you have all of these controls in here to specify how you want it to go cut it. Specify your step overs for each of these parameters that you're putting in here. And you can also control how deep you want to go in terms of cut levels. You could say you only want to go slightly past the halfway point, or you can use these controls in here to step it down. So this is like doing a roughing in layers or levels.
Okay.
And I can say I want to rough it from 4 sides, so I want to basically just cut it past this point here, slightly below the midway point, and then specify engage and retracts, any additional cut parameters, and then generate. So in this process, it's going to create a roughing in levels toolpath, also known as Z-level roughing. So now when you go ahead and hit the play button, it says there's a holder shank collision detected because my tool flute length is only set to 2.5 inch, and you can see there's some, just the holder shank collision that you're seeing right there.
Fine. Yeah.
So I can always go back in here and update my tool definition. Say my tool is about 6 inches in length, shoulder is about 4 inches. I can change the flute length also to 4, save it as to tool, and then I just go back and regenerate this tool path in here. Right click and regenerate, and it'll check for, again, holder shank collisions, and then identify if there is any collision detected. So now we don't see any collisions, as you noticed it. Okay.
That's in a 3-axis.
That's in a 3-axis setup. So your table stays at 0 degrees, and then you're
Right.
programming roughing in levels. So this is a very efficient way to rough it down in levels, because you're just locking the rotary axis and then you're programming it. Now you can also pick a boundary in here to, let's say, define as a containment. So I can basically just create a rectangle by snapping to these 2 points and just go back in here, edit the operation, and select this as the boundary. So you have a lot of control on how you want it to be programmed.
Okay.
So we can also change the step downs. I could probably say I want to take a deeper cut, maybe 80% of the tool diameter. There's the deeper cut I took right there. And then I want to do a machining from the other side. I'm going to introduce what is called a rotate table setup. So this will turn the table over by the specified angle. So I want to do 180 degrees. You'll now notice that the Z is pointing down, which means on your CNC table, the part would be flipped over.
Got it.
And then I can repeat the same roughing operation, do a copy and a paste. And then I'm going to go back in here, and I can change my cut level containment to see how far down you want it to go and cut, and then generate it. So it's going to rough it from the 2 sides. So that's a very efficient way to rough it down.
Okay.
Okay, now I could rotate this back to 0 degrees, or I could rotate it to one of the side orientations to rough some of these material that's being left out in here. You can notice that if you take a look at the right side view, there's some material being left in here, right?
Mm-hmm.
So I could do a simple boundary in here. For example, I could say this is the area I would like to go back and rough. And I can either do it from one of the 2 sides, right? 90 or 270. So I could add a new rotate table setup, and I can go 90 degrees. And I could repeat the same roughing operation in here. And I could select this as my boundary. And I can choose my cutting conditions. I can specify, how far do I want it to go cut back on it. So I can specify that right here. You have these controls, so you can change it. And you can say, where do you want to start the cuts from? And you can specify this also. You can say you want to start right over here. And now when you generate the tool path, you're only going to get a tool path that stays within that area. You see the amount of control that you get?
Yeah, very efficient. Yeah.
Yep. And I can have it go slightly past it here. Now, this feature is what I'm showing you in the demo, is available to you in the expert configuration. Now, our Pro offers a method called re-roughing, so that takes the account what the stock is being left from the previous roughing operation. So in this case, we had to define a boundary. We did it in the expert configuration, but in the Pro, you wouldn't have to define a boundary. If you do a re-roughing, it knows that this was the stock being left from the previous process, so you can go back and rough it again.
So that's like rest machining.
Rest machining, that's available to you in the Pro configuration of RhinoCam.
Okay.
So, the expert offers you the following methods: roughing, parallel finishing, horizontal finishing, radial, and spiral machining in 3 axis. Now, these can also be used as index machining for 4 axis. So like what you're looking at right here. Now I'm going to go back and rotate it to 0 again. I'll put it back to 0. So I bring it to the initial position. And now I want to go ahead and machine these in a continuous operation. So I'm going to introduce 4-axis. We have different methods. These continuous methods are available starting from expert. So whether you have expert or pro, those methods are going to be the same. So I'll use parallel finishing in here. And now I can specify a tool for it. So let's say we want to go with a 1/2 inch tool. And in the cutting parameters, I can specify where do I want the cutter to start at. So I can use the plane control here. You can see that I want to start somewhere over here. And then how far do you want it to go? I can choose like how much I wanted to cut on the other side. So I can specify a containment right here. And you can say you want to do the entire 360 degrees. Now we can't cut below the center of rotation in the case of a 4-axis parallel finishing. So I'm just going to leave it to a very small number in here, like, maybe even like, 10,000s, right? And then I'm going to pick generate. So in this particular step, it's going to create a finishing tool path, but it's not going to cut below these areas in here, as you notice it.
Yeah.
So when I run a simulation, you'll notice that the tool is being perpendicular to the rotational axis.
Okay.
So we programmed most of the areas except this particular section in here where we could not dip the tool below the rotational axis, right, on these areas. So one of the ways how you can program this would be we can do a boundary selection in here. So for example, I could choose a boundary and say this is the, I'm going to turn off the ortho snap right here and pick a boundary around the part. Just create a very simple boundary as you're seeing it in Rhino. So nothing fancy, just using this boundary as an area to contain the toolpath. So now I could go back and do a 3-axis, do a parallel finishing, and I'm going to pick this boundary in here and choose a tool, the same cutter, and I'm going to go parallel to the Y. So I put the angle as 90, specify my step over, and then generate it. So this would actually generate a toolpath with the A being at 0 degrees, and you can go back and finish those areas. So that's one of the ways how you can generate a toolpath in here. Now, you might be wondering, how else can I do it, right? So we have a method called drive surface machining that can be used in a true 4-axis setup. So in order to do that, I would need to model a drive surface and then extrude it. So I'm going to go ahead and create a curved surface in here. So I could be using like a free-form curve, for example. Okay, so I just drew this curve right there. And then I can place this curve where I need to on a model. And then I'm going to use a surface tool. I'm going to say do a surface, and I'm going to extrude the surface straight along this path right here. Okay.
Okay.
Now I could do it this way, or I can even have a slightly larger surface rather than keeping it small. I could make a surface slightly larger in here. So the surface, depending on how you want the surface to be, you can model it here. And I can actually go ahead and say, this is the surface I'm trying to create. You can model the surface. I basically drew a curve, and then I'm going to say surface, extrude planar curve, straight, and I'm going to extrude it right up to this point here.
Why does it have to be a curve? I mean,
it has to be a surface. I'm using a curve to create a surface. That's all I'm doing right here.
Could have been a flat surface?
It could be a flat surface too. Yeah, the tool will be normal to that then. So then the point of doing that would be just a 3-axis would have worked. You wouldn't have to put a curve in the surface.
Okay.
Now, what I'm going to do here is, since I added a surface, RhinoCam flags all the operation as dirty. What I'm going to do is go back in here and say I want to do a 4-axis. I want to do a drive surface machining, and I will pick this as my surface. I want to keep the tool tip normal to that surface. So if I just pick that surface and then go choose a cross axis and generate toolpath, the toolpath is actually going to be normal to the surface only, as you see it, right? But then I want it to be projected to that model. I'm going to choose project the toolpath to the geometry. So it's going to project the path onto the geometry right there for you.
Where did you do the project at?
The project, I chose it in the operation in here. In the cut parameters, there's a project to geometry.
Oh, right there. Okay.
Yep. So let me take the surface. Let me trim a few sections in here. So I'm going to move this to a new layer. I'll say change object layer. And let me actually shrink this. Let me go back in here, make a few changes. The surface is a little too long, so we can actually take this curve that I have here, and I'm going to move this over to, let me grab that curve, this one right here. I'll go to the top view and move it, place it somewhere over here at this point to start at. And now I'll do a surface extrude curve straight. I'll just extrude it right up to this point here. So I'm going to use this surface as my drive surface, right? So I can specify, I want to keep it slightly below the part. That's the area I'm interested in cutting, right? On the model. So I just put it beneath the surface. And now for the drive surface, I'll pick this as the surface so that the tool, the normals would be derived based off this surface, but then you want it to have it projected to the surface that's beneath it. So you want to do a project, and that'll go ahead and project the tool path to that surface. And now if you run the simulation in here, you'll see that the tool is being normal to that surface. And it's projected down to the model, right? So in this case, I could have done a surface that's more like a convex versus a concave, right? And here it's cutting using the side of the, it's being normal to the underlying surface that we created in here. But then it's being following the model. So if you want it to be constantly rotating while you're cutting it, that little undercut section, this is what I would recommend doing it. If you want the A to be rotating.
Okay.
Now I could do one other thing here. I can go back and I can actually flip this over. So select this and I'll say I wanted to flip this over by 180. I'm going to take this and then drag it down into Z. And then I'll check the direction of this. And I want to flip the normal in Rhino. I'll say flip the normal. And now go back into this operation in here. And then reselect this surface. The normals are pointing in the correct direction. And then you want to say project to geometry. So now you'll see the tool path is going to be, the pattern is going to be different in here. So now when I run a simulation, you'll see how the tool is rotating. So the drive surface is that you create is used to derive the normals. And the drive surface that you model has to be normal to your axis of rotation because it's a 4-axis machine tool. And then the tool path is projected to the geometry that you have imported, which is in this case happens to be an STL. So you can have it projected to a mesh geometry, which is an STL is like a mesh geometry, or you can have it projected to a solid surface geometry. So this is resulting in a continuous 4-axis tool path on the drive surface machining.
Why wouldn't you be able to have a simultaneous 4-axis and just like a strict rotary where it would be able to calculate, go past the center line?
Yeah, we have different types of 4-axis toolpath methods. We basically separate them as wrap methods. We have projection methods, and we have true 4-axis or drive surface methods. So in the case of wrap and projection, the toolpath will not be able to dip below the center of rotation. In the case of the true 4-axis, which is the drive surface, you will be able to dip below the center of rotation. Because the tool remains normal to the rotational axis, you can dip below the center of rotation.
So could you do the whole part as a drive surface?
Well, you need to have a surface that's normal to it all the way across. So not for this particular part. The answer would be no, not on this part.
Okay.
Only you can do maybe the top half of it, but not the underside. So you'd have to, so the best way to do this would be to do the finishing like we talked about here. Now when you output it, it'll all be just one piece of code to the machine. It's not going to be split up into multiple programs.
Okay.
So when you run it, it'll be just one piece of code. So now when I post this drive surface machining here, you'll notice that it's moving in X, Y, Z, and also your rotational axis. So it's not just two linear and a rotational axis. If you take a look at this code here, you'll see that the y is also, it changes the x, y, z, and a. So it changes as you're cutting it. So you can see that the y, there's changing in. So typically when you do a 4-axis toolpath, in this particular case, it'll just be a y, z, and a. The x would remain constant. When you do this 4-axis parallel finishing in here, if I post-process this, since the tool remains normal to the axis of rotation, your x would remain constant.
Okay.
And the y, you can see the x remains at 0. The y, z, and a is the one that changes. So we have 2 linear and a rotational axis when you do like a 4-axis parallel finishing, which is like a projection type of machining. Whereas when you did the drive surface machining, you're seeing that all the 3 linear axes could be changing, and the rotational axis. You can see the x is changed, and then you have a y and a z, and then if you look down the program here, your y also changes.
Okay.
So that's a true 4-axis method versus in a continuous or projection type of method. So all of these options are available to you. Now to machine this particular feature, I would either do it as a drive surface machining, or I could do it as a indexed operation by just doing a parallel finishing by defining a boundary.
When you purchase the software, is there a user manual that explains all these different operations or anything that goes with this?
Yes, there is access to what's called a learning tab. You have a quick start guide. You have a online help, which basically gives you a description of each and every method in here. So when you select the help, even with the demo, you can have access to all of these.
Okay.
You can learn about what each of these methods are and how to best use these methods. Now, we also have several video tutorials that are on our website. And if you add on our maintenance program, you'll also have access to what's called a CAMJam video guide, which gives you several instructional videos. And also we do webinars each month. Those are more like training webinars, and we talk about how to best use different techniques. And those webinars are also made available to you. If you're not able to attend the webinar, the webinars will be recorded, and also you can go back and review those recordings anytime. So those are additional benefits that we offer for customers who are on our maintenance program. And on top of it, you also get the version upgrade, so you wouldn't have to pay for a version upgrade when you're current on your maintenance. So you will have access to the latest versions.
Got it. There was one other thing I noticed too on the demo, that the mesh. Is there any reason to bring the mesh in and to repair it or fill holes or anything like that? The demo on the mesh didn't work, and I saw in one of your YouTube videos to go back and remesh it and clean it up into better triangles.
Yes, the mesh module is great for when you're working with like point cloud, or if you want to fix a mesh, repair a mesh. If you had a lot of holes or the model was not very clean, you can go back and repair that. So that's an add-on to any of our RhinoCam products. So you can just go from the mill module to the mesh module in here, and basically you can analyze the mesh. So you can go in here and perform a diagnostic run and see if there are any open edges on the mesh. So I can do a check right here.
Yes, so that's on the demo file.
Right. So in the demo, you can't perform any of these tasks because the mesh module requires a license to run any of these commands. And here you can see that it shows there's about 80 open edges right here. So I can do in this particular model, it wouldn't make much difference because you're not going to be cutting it from this direction. So the cutter wouldn't be entering in from here. But if you want to cap this, you have tools where you can do an auto fix to automatically, cap these holes. You have also tools where you can remesh it, make the mesh more uniform, or if the mesh is too large, you can decimate it in here. So for example, if I select this and do an auto fix, it'll automatically fix for holes, self-intersections. You can see it automatically capped it here as well.
Got it. Okay.
And you can go back in here and check. You can basically see the mesh is about a little over 8,000 triangles, so it's not a whole lot. But if you want to go back and remesh it, or if you want to use some of these mesh tools in here, there's reduce mesh, mesh smoothing, remeshing. All of these are available in the mesh add-on.
Okay.
And once you have all of these operations programmed in here, you can basically save the file in Rhino, and saving the file in Rhino will automatically save all your machining operations that you put in with the 3DM file. So you're not creating any additional file formats in here. So you're basically just saving it to this file. And then finally, you want to do a post process. So in this particular step, we actually programmed a parallel finishing and a drive surface in addition to the 3-axis method. So I can suppress, saying I don't want to use the parallel finishing. I'm going to suppress this. And then now I'm going to finally do a post all. And before I post it, I can look at the time it's going to take for each and every operation, depending on the feeds and speeds I put in for the roughing process and then the finishing process. So you can go back and optimize your feeds and speeds. So the number I put in here was way too low for if you're cutting wood or any softer materials. So you can always go back and update your feeds and speeds and recompute the estimate of the time.
Okay.
And then finally, you want to do a post process. Select post all. In this case, it's going to post all the operations out to the machine. And the posted code will have the entire set of G code. It'll output the rotation for each and every step. So in this case, you can see the A is 0 here, and you can do a search for the A. It'll do a 180. You can notice that the A turns 180 degrees and then goes and rotates it again 8 to 90 degrees to rough it from the sides. And then when you go back to A0, it starts the 4-axis parallel finishing, goes from 0 to 360, and then you're doing the 4-axis drive surface machining operation.
Got it.
So you can post all to one NC file and send it out to your machine tool.
Okay.
Now this entire workflow, what we did here, if I'm going to be working on similar type of parts, I can save these operations into a knowledge base. So I'm just going to go ahead and put it in this data folder. And let's go ahead and open up one of the other files in here. So I have this saved. And let me go ahead and load this other model.
Yeah.
And now I'm going to just go ahead and do the same thing here. Define the put the 0 right up to the center point. And if I need to rotate the part, I can just do a flip it over. And I can check the size, do a box stock. It's about 96 by 614, so I need to probably scale it down here. It's too big, right? Yeah. So I can do a scale. I can say 0 and maybe 0.039, maybe it's in millimeters here. Oops, I didn't scale everything in here, looks like. Yeah. Okay, so let's go back and check the size. It's still 37 by, okay, I need to scale it down by 10 times. Okay, that looks reasonable. 3.7 by 24 inches.
Yeah.
So I can define the stock material in here, maybe go with 4 by 4, and then maybe 26 inches. So the process is very similar. Once you do it, you align the stock, and then you establish a 0 location. And now, rather than having to go through the process of creating the operations from the menu, I'm just going to say load my knowledge base. I'll find the knowledge base I had created for the previous project, and I already have it here. So now I can say the roughing operation, I would like to just see all the parameters in here, just generate the toolpath. So I can just verify if I need to make any changes or adjustments, I can do it and then regenerate it. So you're basically creating your template of operations for your workflow, and you'll now notice that how easily you can adapt it to different operations. So
you rough that in a three-axis rough.
Yes.
And then would you turn it, since they're all 4-sided, you turn it 4 times?
I could just do it from 2 sides because if there aren't any undercuts that, you can just do it from 2 sides.
Okay.
And then I can go back and do the finishing operations in here. Start with the 4-axis parallel finishing. In the cutting parameters, I can set my low and the high value. See where you want it to start. And then the high value, I can basically put in So how far you wanted to cut right there.
Yeah.
Generate it. So in this case, there aren't any features that are cutting below the center of rotation. So you could, you might as well just do it in one operation in here.
Yep.
So we put in all the time and effort in programming the part number one. Now the workflow is a lot simpler and easier.
Yes.
Because we are using a knowledge base to take advantage of the entire workflow.
There's one question I wanted to ask you too. When you first set up the machine, you had the table position, whether it was a table or a head.
Mm-hmm.
I would have assumed that it would have been a head rotating instead of a table.
A head rotation, that's a good question what you asked. A head rotation is typically used where the part remains stationary and the rotation is on the spindle where the head tilts from, like for example, minus 90 to plus 90. So consider you have a CNC router where you're basically, it's similar to like a 5-axis, but there's only one rotational axis on the head. So the spindle can tilt from minus to plus 90. So that's where it would be a head rotation. So in this case, it's a rotary table where the part turns and the this tool remains normal to the XY plane.
Okay. Yeah.
So that would be a rotary table. And all of these 4-axis methods that you see here are designed for rotary tables and not for rotary head machining.
Got it. Okay.
So you can see that in just a few steps, we were able to program it. If you want to go back and make changes, you can always edit these parameters in here and just go back and regenerate the toolpaths.
As long as it doesn't go below the neutral axis or the central axis, then you could get by with the 3-axis and the 4-axis parallel finishing.
Parallel finishing, well, the indexed machining can go below the rotation center. So only the continuous methods like 4-axis parallel finishing, where you will not be able to cut below the center of rotation.
Right.
But then you have other ways to efficiently go back and just program those areas by just defining boundaries.
Got it. Yeah, I see that.
So you don't have to machine the entire part. You can just create a small boundary for that section. You can either do the drive surface machining, like we talked about, or you could do a indexed machining where you just throw in a boundary and then use a 3-axis operation.
Okay.
You can also rotate it to like a 45-degree and then machine it if you have undercuts in a different location.
And using the drive surface in there would allow then the A rotation to occur, where if you did strictly 3-axis, then it would just.
That is correct. The A would be basically locked to a given orientation, and then you would be programming it.
Got it. Now, are you going to post this to YouTube?
The video we will put together, we'll edit it and have it posted onto our YouTube channel. Yes, and we'll try to make a link available to you as well.
Yeah.
If I can get the raw video link available to you first, and then we'll edit it and compile it and put it on YouTube.
Great. Then I can go back and review that drive surface there. That's good. Thank you.
Any other questions in the demonstration today, Steve?
No, not right now. I got to go back and do it myself and make sure I got that done. But no, it was great. Thank you.
Okay. Give me just a moment. I'm going to go ahead and pause the recording in here.